We are talking now about Bayesian classification. So we are applying the Bayes rule for classification that way, in the sense that we are getting the same equation that we had before, but now we're in the context of multi-class classification. So we have the posterior probability here, which is given according to the Bayes rule. And then when we develop the evidence on as a denominator, we got that thing. So this is the usual application of Bayes rule for classification. So the corresponding discriminant function we achieve with that is it is the same for all the classes, and it boils down to a function hi. The hi here is the discriminant function for class Ci. And as such, given that the evidence is the same for all classes, we just get rid of it. We just keep what was on the top as the numerator in the formulation here. So we got the likelihood of getting X from class Ci here times the prior probability of getting a sample from class Ci. Applying the log on that, we are changing the function, but that's okay in the sense that it is not changing the order. What was the maximum hi here will be the same with that. It's just that we are applying the log on h here. So we've got log of PCI, Px given Ci, given class I, plus log of the prior here, which correspond to that. So by applying the log here, we got into that formulation. And when we assume that the likelihood follow, so the sample X for a given class is following a normal distribution. So we have a normal distribution per class. We have so a normal distribution that is parameterized by mu I, which is the mean of the distribution for class I. And we have sigma I here, which is the standard deviation of the samples from class Ci according to our modeling we are making here. We've got something like, okay, the P of X given Ci, so the likelihood for a normal distribution per class is that thing. So this is the basic normal distribution formulation that we all know well. And given that we are using this in a log here, we are simplifying this equation like this here. So basically, we are having minus 1/2 log 2 pi here, which is that part. Then we have minus log sigma I, which is basically that thing with a log. Minus here we have X, we have that thing here, X minus ui squared divided by 2 sigma I, which is what is within the exponential, because basically the log cancel the exponential. And we have a last term here, which is log of the prior, which is that part here in the equation. So this gives us the new hi. So this is a kind of description of the discriminant function that we obtain when we are modeling the distribution of each class as a normal distribution with different parameters, different set of parameters per class. As example, let's suppose that we have a data set here, a big data set, big X here, made of X and RT over several classes. And this RT here is in fact a 0, 1 odd vector. So, a 1 odd vector, in fact, where we have one value equal to 1, so one RT here. This is when xt is from class Ci. Otherwise, the RT is equal to 0. That means that the sample xt is not coming from class Ci. So when we are estimating the prior probabilities, we are able to do this simply by summing the RT over the n. So we are counting the number of samples that are coming from class Ci in the data set divided by the overall number of samples there. For estimating the means, so the mean of each class, so for class Ci, the mean is computed as this thing. So this is interesting because now we are using the RT as indicator to use or not the samples. So we are summing over all samples. So this sum is made over all t's, but in fact, we are using the xt only for those where the RIT is 1. So for the situations where the XT is associated to the right class. For the other classes, when the XT is associated to another class, the RIT is equal to 0, such that we are not taking into account this. So basically, we are summing all the XT from class CI with this equation on the top, divided by the total number of samples in class CI by summing the RIT. So this RIT formulation with a RT that is a vector with a one-hot vector encoding is super interesting in terms of simplifying the formalization of the problem and getting with such equation for computing the mean for samples from class CI over the complete data set. Likewise, for the standard deviations, this is computed that way. This is basically the same equation we have of estimator, maximum likelihood estimator of the standard deviations, but using the RIT here in order to enable the XT when this is coming from class CI, and we are dividing over the number of samples from class CI in the data set. So this is still a bias estimator. We are not using this -1. We are using basically the value of n, where n is the number of samples from the class. So the corresponding discriminant function is basically the same, except that we replaced the mu and the s by the m and the mu and the sigma by the s and the m and the s. So we are using the estimation of the means, estimation of the standard deviations instead of the real values, because in practice, we don't know the real values. We are doing classification, we are doing machine learning, so we need to evaluate these parameters from the data. And so just replacing mu by m, replacing sigma by s, so by the estimator, we've got this equation, which is the same than we had before with this replaced. We can do some more simplifications over that equation. First, we know that this part, -1/2 log 2 pi, is a constant. This is the same for all HI. So basically, we don't care keeping this because all HI will be affected the same way. Then we can also assume, so the first simplification is basic. It doesn't change anything. The second one, we can assume that the variance is equal for all classes, but the mean will be different. So this is a stronger simplification. It changed the model, but it gets us to say that the sigma I is the same for all the classes. That will simplify several things. And we can also suppose that we have the same prior probabilities, the same a priori here with the p hat. So basically, we see that we have about the same number of samples from each class. This third simplification can be acceptable, although it kind of simplify this on some aspects, especially with unbalanced cases where this is not true. So by doing these three simplifications, it boils down to what we call a closest mean classifier, which is probably the simplest classification model we can think, which basically assign the sample to the closest mean, having one mean per class. So we have, like, if we have 5 classes, we will compute the 5 means, one mean per class, and then we will compute the distance between a sample and each of these 5 means, and we'll assign the sample to the class with the closest mean. So this is a rather simple approach, which get us with an equation HI, which is that thing. Basically, we want the HI to be maximum, so we want to minimize the distance. That's why we have a minus sign here, and we take the distance between X and the center of class CI, which is MI. And from that, we are able to say, okay, let's assign this sample X to the class CI, the one that is minimizing that distance. So if we look at the likelihoods of 2 classes with the same variance here, we see 2 normal distributions, 1 per class. So we have the probability density function of this class. We see that the sigma is the same. So the sigma for the red and blue distributions is the same, is equal to 2. We have the same also prior probabilities at 0.5. The difference is lies in the means, which are different, -2 for the red ones, red curve, and 2 for the blue curve, so the other class. So this, you can see this as the likelihood for each class. So this is a distribution. So we say data from class red here follow the red curve, basically, and data from the blue class follow the blue curve here, approximately. So this is the likelihood on the top, and at the bottom we have the posterior probability here, which is a probability of assigning data to class red or blue, depending on their probability. So we see here that on the right side, the probability of being from class red is going quickly close to 1. So basically, when we have an X that is negative, we assign this to the class of red. When we have an X that is positive, it's getting close to 1, 0, also for the class of blue, the blue class. And in between, we have something that is varying around 0, and we see that at 0, they are crossing. So basically, we can use a threshold that's saying, well, when it is over 0, the X is over 0, it is class blue. When it is below 0, it is class red. And the decision threshold is at 0. So this is a special case. In the general case for the closest mean classifier that we saw just before, this is the boundary is when H1 is equal to H2. So in the case of the closest mean classification, the threshold is at M1 plus M2 divided by 2. So we are looking at the middle point in between the two means. So here we see that the first one is -2, the second one is 2. So 2 minus 2 is 0, basically. So yeah, that get us with that threshold that we are making a decision based on a threshold, which threshold here is 0. It can be something else. If we were using different distributions with the same variance, the means would be different. So the threshold will not necessarily be 0. It will be at the point where the posterior probabilities are crossing. So here we have another case where then the variance is different. So we see that, again, we have means of -2 and 2, like we had before, but the standard deviation, the variance is different. So we have 2.0 for the red and 4.0 for the blue. And we even have also different prior probabilities, 0.8 for the first class and 0.2 for the second class for the blue. So here in that case, we can see the likelihood on the top here. And when we get into the Bayes rule, and we have now the posterior probability, which is kind of informative because we see, in fact, that there are 2 points where the probabilities values are equal. So 2 points where the curves are crossing. We have this one here, which is, I would say, around -8.5 or 8.7, something like this. And we have the other one here, which is about 2.3, something like that. So these are the 2 thresholds that we should use when we see that it is between the first and the second. So I would say higher than -7, 8.7, something like this, but less than 2.3 something. It is from the class of reds, because this is where the posterior probability is the highest. While when we are outside that zone, so that means here and there, we have an highest posterior probability for the class of blue, the blue class. So this is how we will assign samples in that region.